All right, lesson 15, day 1. All right, understanding systems of equations. So our overall question for this lesson is, how can graphs help you find the solution of two linear equations? Well, in our previous lesson, you learned the structure of linear equations that have no solution, only one solution, and infinitely many solutions. Now you will examine the graphs of pairs of linear equations to see if both equations have a common solution. So this lesson is focusing on a system of linear equations, which is two or more related linear functions for which you are trying to find a common solution. Go ahead and circle, highlight, or write them in your notes. Write this definition in your notes. All right, so the problems you'll work with in this lesson have two equations and two variables. To solve a system of equations, you need to find the order pair or pairs that solves both equations in the system. One way to find the solution is to graph the equations on the same coordinate plane. So just like we talked about in our last lesson, there are three options for the number of solutions an equation or system of equations can have. It can have one solution, no solution, or I probably didn't need to write or infinitely many solutions. So we want to learn or mesh together what we learned in lesson 14 with lesson 15. So in lesson 14, we identified some easy ways to categorize the different systems of equations. With one solution, we said that the variable terms will not match. Meaning they have different coefficients. With no solution, they had the same coefficients, same variable terms, but different constants. And then with infinitely many solutions, every single term matched. Hopefully that's bringing up some memories for you. All right, so let's mesh that together with what we're saying in lesson 15. So with one solution, if the variable terms match or the variable terms don't match, which means they have different coefficients, one solution is going to mean, really in this lesson, that they have different coefficients, which equals different slopes. Okay? And again, the slopes could be anything, okay? It's not like they have to be opposites or perpendicular or parallel. We can just say they have different slopes. This one that we're talking about here, for this first example, example 1 here, we can see that these two lines, when they're graphed, are parallel. And we know they're parallel because they can keep going on and on forever and ever without touching. So they never touch. If they never touch, and we just talked about the definition for the system of linear equations, if they don't have a common solution, then they have no solution. Okay, so if you have a set of parallel lines, this is automatically no solution for this system of linear equations. All right, and then we're going to prove that by putting together what we did in our last lesson and matching that with the no solution that we learned. So last lesson we learned that no solution means they'll have the same coefficients but different constants. If you look here at these two equations, they both have the same variable term, which was 3x, but their constants are totally different. For this bottom one, of course, the constant is -2. But for the top, there's nothing there, so you can actually just put an invisible 0 there as a placeholder. So they have the same variable terms, the same coefficients, but different constants, they will never touch. So in this lesson, we'll learn that no solution, or we've just learned that no solution means they have the same constants, same coefficients, but different constants. We already knew that to be no solution, but they will end up being a set of parallel lines with the same slope. Okay? And then, of course, that leaves our last one of infinitely many. I'm going to erase this stuff that I wrote before because it's just kind of crazy looking. Okay? So with infinitely many solutions, as you can imagine, we talked about infinitely many solutions. That one's going to mean that, just like what we said last time, they're going to have everything match the same coefficients, same constants. They'll be the same. They'll have the same line. Well, they will be the same line with every single solution. Everything will work for it. So what that means is that they are the same equation. Same equation because everything matches, or every term matches. Same equation, same line when graphed. Okay? And then we're going to be able to match our graphs and our equations together and just figure out what's going on here. Okay? So you're just putting together what we did in lesson 14 with this current lesson. We're just giving what we've been doing a name. All right? That's all that's new this lesson. So in this first example, of course, we saw they're parallel lines, so they'll never touch. Since they're parallel, they have the same slope. Oops, let me bring that down. That means that these two lines have the same slope, but obviously they don't have the same y-intercept or the same constant. So that means that they are parallel. And it also, of course, means that it's no solution. Okay, they will never touch. They're almost like mirror images of each other. All right, so reading this at the bottom, just to summarize what we just talked about, these lines don't intersect, so there is no ordered pair that will satisfy both equations. There is no point that lies on both lines. Like an equation that has no solution, this system has no solution. All right, so they said circle the two variables that are used in the system of equations. Of course, you saw that they were x and y. All right, moving on. All right, example 2, graphs of two linear equations might intersect at exactly one point. If they say it just like that, if it's exactly one point, that means there's one solution. And you should be able to tell me about it being one solution. One solution just means that it's going to have different variable terms or different coefficients, which means they have different slopes. When they have different slopes, they're going to intersect at some point. So here is a graph of a system of equations with exactly one solution. The point where the lines intersect is 0, 3, which we see here. So that means it's a solution to both equations. So that means wherever these two lines intersect is where you have your solution. So the solution to the system of equations is where the two lines intersect, or they cross, okay? Intersect just means they cross each other there. All right, so like an equation that has exactly one solution, this system has exactly one solution. So that means you can substitute 0, 3 into both situations or both equations to verify that it is a solution to both. So for 0, 3, where they saw an x, they put a 0 in its place, and where they saw the y, they put a 3 on both equations. And they found that once they plugged that point in, they got a true statement at the end. Okay, so that means it is a solution to the equation. All right, moving on. Two graphs of two linear equations might intersect at all points. If they intersect at all points, that is infinitely many solutions. And remember what we talked about last lesson is if you have infinitely many solutions, every single term matches. Which means, of course, that the equations match. And we want to put in that the equations are going to match once simplified. So let's make sure. So they gave us these two equations. We have y plus 2 equals 2x and y equals 2 up against x minus 1. If we simplify both of the equations and put them in slope-intercept form, that's the best way to see it. Let's go ahead and do that. So for the first equation, we're just going to move our positive 2 to the right side, to the right side. So we're actually just going to subtract it from both sides. So we'll have y equals 2x minus 2 is our simplified equation in slope-intercept form. The other one, all we're going to do is just distribute the 2 to both terms inside our parentheses. So we'll have y equals 2x minus 2 as well. So of course you see that they are the exact same. They are equal to each other. Since they're equal to each other, every term matches. So the equations match, of course, which of course gets us back to everything having, or to these being infinitely many solutions. Any single point we choose will make this a true statement. Okay. All right. So any point works. All right, and I will leave this reflect question to you. Thank you.